Hello, I'm John O from StradVision. Pleased to meet you all. StradVision develops deep learning-based vision software for autonomous vehicles, and we're excited to participate in CVPR with NVIDIA this year. Let me show you a few examples of what we do to bring safe and reliable autonomous driving to everyone. This is a pedestrian detection example with instant segmentation in an urban area. This is a lane and object detection example on a snowy highway. This is a surround view monitoring example using multiple fisheye cameras. And we're detecting a bunch of cows here with our animal detection function. Pretty cool, right? As you can see, we enable cameras to accurately recognize objects even in difficult conditions. We have been a close partner with NVIDIA since 2016 and have 9 million vehicles in production using our novel SVNet perception solution. To highlight StradVision and NVIDIA's capabilities, we prepared a special use case to highlight what a combination of AI vision software and hardware can do. Alright, though we're all trying hard to beat the COVID-19 pandemic, it's still running rampant. It's important to be mindful of your surroundings and play it safe, by avoiding crowded areas or at least keeping a safe distance from people around you. Accordingly, for CVPR this year, we tried out a new function using SVNet's object detection and distance estimation functions to see how the algorithm can help people and the society at large to beat the pandemic. To start things off, we embedded our perception algorithm SVNet inside NVIDIA's Jetson AGX Xavier. The reason we chose Xavier to run this feature is due to its robust flexibility and performance. It's much easier and faster to implement SVNet since Linux is already ported and the CUDA library is robust. Also, the ease of adjusting the deep learning-based network and its size is a critical factor when deploying SVNet in the real world. To start things off, by using a single front-facing 8-megapixel camera, we got a raw footage of a busy urban street at nighttime. Though the recording was done inside a vehicle for this demo, we developed this application with surveillance in mind. So it also works on a much elevated position with a different angle, with a simple camera parameter tweak. So with the video input, we then enabled object detection and distance estimation functions to assess the relevant objects in the scene. As you can see, all the detected objects have bounding boxes around them, with the distance value labeled down bottom in yellow. In case you're wondering, the white lines you see around the vehicles and pedestrians is the instant segmentation function. Okay. With the object and distance data, we then created a bird's eye view map of the scene on the right, mapping out all the relevant objects within 15 meters of the car. Also, each object in the map is tagged with its coordinates, unique ID, and object type in relation to the vehicle down bottom in blue. Also, on the left side, you can see an object counter being updated in real time. The network we deployed here can detect a total of 9 different objects: pedestrians, bikes, sedans, trucks, buses, traffic lights, as well as circular, triangular, and square-shaped traffic signs. Once the camera mapping is done, it's quite easy to identify the relational dynamics and proximity between all the objects identified on the map. Finally, based on all the data, we then added a 2-meter distance threshold to pedestrians, and based on this rule, SVNet enabled our counting the social distancing rule violators, as you can see on the bottom left. This was an example where a robust deep learning-based embedded perception algorithm can be deployed to address real-world challenges swiftly through powerful hardware. And that's about it. I will look forward to virtually meeting you all at CVPR, and of course, stay safe.